Hello, good evening, everyone. My name is Wolf, and we are here for the July edition of an Introduction to Astronomy that I've titled Sights of the Cosmos. This event is part of a series of public events that the San Jose Astronomical Association is bringing to you. And yeah, it's an introduction, so it's intended for people who are new to astronomy or new to SJAA. But if you're already into astronomy or already a member of SJ and you're here anyway, that's great. So thank you all for attending. I really appreciate you all being out there in internet land, joining us for the next hour or so. I appreciate that. So Sights of the Cosmos is the title you see here, but I actually have an alternative title for this presentation. I also call it Stuff in Space, What We See and How We See It. So we will talk about the kind of things we see out in space, and also the how we see it portion will be important as we go through the next hour. All right. As we go through the session, feel free to ask questions via YouTube chat. There is someone else on the line who's helping with us. I'll do a quick introduction. Hey there, Swami. Swami, you can say hi to the group.
Hi, everyone.
Thanks, Swami. So Swami and I will be your hosts for the evening, and Swami will watch the YouTube stream, the chat stream, and we'll take a few breaks throughout this session for Q&A. Thanks, Swami. Okay, so yeah, please feel free to ask questions. And also, before you log off tonight, before you end your time with us, please do give us your feedback about what you thought of the show. We do appreciate your feedback. We use that to help make these events better. So, all right. One tip for you, we're going to be talking about outer space. Outer space is dark, and so some of the images that I'll show will probably look better with YouTube's dark theme. So if you haven't tried this already, you may want to give this a shot. So if you within your YouTube window, if you find your little avatar icon in the top right corner, here it's the little sun image in this particular one, you can click on that. This menu should pull down. In the middle of this menu will be this dark theme option. If you click on that, you'll get a different little pull down window where there's a slider down here. And you can click on the slider and that should turn on dark theme. So you may like that. Give it a try. It's entirely up to you. A quick word about SJAA before we really dive in today. So we are an educational organization and a nonprofit. We run a whole bunch of public programs. Ordinarily, we do public star parties out in dark site locations as well as within San Jose. We have a program that's the school star party program where we go to schools and host star parties. We have a bunch of public talks, introductory talks like this one, and also more advanced science talks. We provide help with equipment if you have telescope sitting somewhere in the back of the closet and you want to dust it off and get it working, we usually help you with that. And we also have swap meets, which are great events to pick up, some previously used equipment. For members who have actually joined SJA for only $20 a year, I think of that as the price of a pizza, not too bad. We have imaging workshops, we have training that can help beginners get going. We have a loaner program where you can check out cool equipment to try it before you make investment in your own purchases. We have a nice library where you can get books, and we also have a bunch of private observing events. But now, of course, because we're all dealing with COVID-19, some of these things are currently on hold, so we cannot hold our in-person events, and instead we've been experimenting with these kinds of online events like this one, trying to nevertheless bring you some content while we're all stuck at home in front of our computers. So yeah, okay, so please, thanks for being here for this one, and please check out our other online events like our armchair star party. If you want to get more information, there's our website, sj.net, and then there is the meetup group here, meetup.com, SJ Astronomy. That's probably how you found us today. And normally we are physically located in downtown San Jose in a place called Hokie Park. So I hope that at some point in the future, maybe I can meet you there at an in-person event. Okay, and before we jump then into this particular introduction to astronomy, I want to give a quick pitch for the other introduction to astronomy that we also offer. There is another presentation that we give roughly the same time slot in about 2 weeks. It'll be Intro to the Night Sky. It's presented by a different member of SJA, someone named Dave, and that introduction focuses more about the constellations you see in the night sky and things like that. And I think of what I'm going to talk about tonight, and Dave's Intro to the Night Sky is very much complementary. So if you haven't checked out the other one, check that one out as well. They go together nicely. All right, here's an outline of what we're going to talk about today. But I always think this looks way too much like an outline for a business presentation. So let's just skip over this. And instead, I like this picture, right? So I think of tonight as kind of an astronomy sampler. So there's a lot that astronomy has to offer. And I think of this as a taste test for you. So I hope I can give you some samples of stuff here and there, and maybe some of it you'll especially like, and that'll be something that maybe you can pursue further in the future. So yeah, so please enjoy your astronomy sampler taste test. So let's get started. 1 second. Yeah, so Swami has a comment. So let me. Yes, Swami, what's up?
So, Wolf, there is some feedback from one of our audience members on YouTube saying that there is a high-pitched whining sound. Not too bad, but maybe good to know. So, I don't know if you know anything about what's causing it.
Okay, that is a good question. I do not actually. I do not notice that in my equipment here.
Okay.
Okay. So okay, maybe we can keep a tab on that, right? If that does not go away, if it does not clear up, please let me know, and then maybe I need to reset some things. But yeah, from my side, I cannot observe that right now.
Okay.
Interesting.
Sounds good.
Okay, so my apologies to folks who have to put up with that right now. Let's see if that clears up. Okay, thank you, Swami.
Yep.
Okay, yeah, stuff in space, right? So if we think about the movies that we tend to see in the theater, this is the kind of stuff we see in space, So here's a nice collection of pictures that I clipped from different movies, and I challenge all you out there on YouTube to help me identify what these different objects are. So maybe you can just kind of shout it out into the YouTube chat, if you will, right? So for example, what's the one here on the top right, or the one on the middle left? Some of these may be a little more challenging. There's also a few easy ones here, right? Top middle, I think you can all tell me that this is the Death Star from Star Wars, and of course on the bottom we have the Millennium Falcon. But there's a bunch of other ones here. So again, help me out, help me identify these. I'm testing your nerd cred. But in any case, these are the things that we see when we watch our sci-fi movies. And these are all really cool things. But when we do look into space with our telescopes, we actually tend to see stuff like that. And there are no spaceships here, which is on one hand somewhat unfortunate, but on the other hand, I do think that these are all really amazing, beautiful images. And we will talk a lot more about this as we go through the next hour. So there's lots of stuff ahead in this talk, because there's a lot of different stuff in space. Again, like I said earlier, please ask questions, and if you're lucky, I may actually know the answer. I should point out I'm not really an astronomer. I'm just doing this stuff because I think it's cool, and I hope I can share with you some things that maybe you think will be cool also. Don't worry about remembering everything that we're going to talk about today. Mostly just enjoy the show. Oops, I forgot to fix something up on the slide, but that's okay. I do have an assignment for you. Pick something from this talk and ask someone about it later. And here I wrote maybe at tomorrow's Armchair Star Party, but actually there is no Armchair Virtual Star Party tomorrow, but there will be one coming up in the not too distant future. So, you can still think of a question and maybe ask it there. All right, let's ask the question of, or answer the question of where we are. So we are here, and here is, of course, on planet Earth. We all know this thing, right? We live, somewhere up here. But usually from the times when I give this talk in our physical location in Hoagie Park, I know that there are folks in the audience from all over the world. I myself was born in Europe, somewhere on this other half of the globe in these pictures. So yeah, this is our home, the Earth, right? We're all familiar with it. And if we zoom out a little bit, we can include the moon into this "you are here" picture, right? So this is part of our home, the Earth-Moon system. And here's a picture of the same system, except it's from a different perspective. This is a historic picture. This is a little over 50 years old now. This was the first time the Earth was imaged from the perspective of another world. This was from Apollo 8, as Apollo 8 orbited around the moon and saw this historic picture called Earthrise. So yeah, this is kind of a fascinating picture from about 50 years ago. But neither this picture or the prior one really give a good feel for how far apart the Earth and the moon really are. In historical times, there were times when people thought that, hey, maybe the moon is only like 100 or 200 miles up. Maybe we could even reach it if we climbed a tall mountain, right? We thought that at some point because we just did not know. But we do actually know now that it's about this far apart. So here's a picture from a spacecraft that we have launched out into space, that as it was receding from the Earth-Moon system took this picture, and this provides a much better perspective of how far apart these two objects really are. Okay, and then if we take another step back, we can say we are here in the solar system. So here we are on the Earth, the third planet out from the sun, and here are all the other planets, starting with Mercury on the inside, going out to Pluto. So this is a pretty picture, but it's an artist's rendition, and it's really not correct in terms of sizes and scale. So this image is a much better representation of size and scale. So here the relative distances between the objects are essentially correct. And so one interesting thing to note here is that the first few planets, right? So here we go. Here's again the Earth, right? Mercury, Venus, Earth, and Mars. The first four rocky planets, they're actually very close to the sun, relatively speaking. And then things really spread out. There is a little marker here by the Earth. This is what we also call 1 AU. 1 astronomical unit is the average distance from the Earth to the sun. We'll talk about that more later. And then you can see that Saturn is like 10 AU out, so it's 10 times as far away. And all the way up to Pluto, we're about 40 AU away. So yeah, so the solar system really spreads out as we go to the outer planets. And also, the sizes of the dots are correct relative to each other. So the Earth is pretty small compared to Jupiter, for example. Right? So this picture gives a much better idea of the relative distances and sizes. And I hope that's one thing I can convey to you today during this next hour, just how big stuff in space really is. Okay, let's take another step back. And we can say, well, we are here in the Milky Way galaxy. And if you've ever been at a really nice dark site in the summer, you might have seen a picture like this. So I did not see the Milky Way galaxy until I was in my 30s, and that was really too late. So if you guys have not seen the Milky Way on a really dark night, go check it out. It's a beautiful sight, and yeah, so this is the Milky Way galaxy. But let's see. If you were to look at it from the outside, it would look something roughly like this, right? So this is kind of a flat structure with a bunch of stars in it. Now there's a little note here that says not our actual galaxy, because we have this problem of being inside the Milky Way and we cannot travel outside it to really look at it from the outside. So yeah, we're just stuck inside it, and so we have to take some educated guesses about what it looks like, and we'll talk about that a little bit more in a moment. But I want to make sure we take a step back maybe and ask, wait, what's a galaxy really? Because I know that can be confusing for some folks. And so like I said a moment ago, a galaxy is many, many stars, and they're typically arranged in a flat spiral structure. But even here, there may be another question to ask. Just wait, what exactly is a star, right? I know that also creates a little bit of confusion sometimes. And so let's answer that. So here's a picture of our sun in the daytime sky. If you were outside today, you would have seen something like that here in the Bay Area. And if we look at the sun from outer space, this is a picture of the sun from the International Space Station, then it looks like this. So here is the same sun now against a black background, because there is no atmosphere to provide the scattering that gives us the blue sky that we see here from the ground on Earth. So yeah, so here's our sun from inside our atmosphere and from outside where the International Space Station is. Now here's a picture that an SJA member took in the winter time some time ago at a place called Pinnacles National Park. It's a nice picture of the night sky. And let's focus for a moment on this one star right here. There's one bright dot here, and if we were to look at that one much more closely, it would look like this. And you may go, hey, look, this bright dot looks a lot like this bright dot, and that is in fact what's going on here, right? So it turns out that our sun and other stars are really the same kind of thing. This is actually not something that we've understood throughout history, right? This is a relatively recent revelation from about 100, 200 years ago. So, understanding that our sun and other stars are the same type of thing is not something we've known for all that long. Okay, and then here is a collection of stars that we call star clusters. So here is a few thousand stars that we can see within our galaxy. So if we point our telescope in the right direction, yeah, you can see this beautiful picture of thousands of stars. And then going back to a galaxy, this is billions of stars arranged in this flattish, spirally shape. And so in our galaxy, we've about 2 to 400 billion stars, right? So yeah, if you were to count all the stars, that's how many we're talking about. It's a lot. But like I mentioned earlier, this picture I'm showing is not really our actual galaxy, because we're stuck inside it. We cannot go outside. But we still know quite a bit about how it is really shaped. And so you can kind of think of this analogy. Imagine for a moment that you were stuck inside your own house. And given all this coronavirus craziness, maybe that's not even that hard to imagine, right? So let's say you could not go outside your own house, and you wondered what your house looks like from the outside, but you cannot go out and see it. But you can still learn a lot about it, because you could walk around your house and explore the floor plan, and you can look out your window at other people's houses, right? And by exploring your house from the inside and exploring other people's houses visually by looking out your window, you can create a pretty good image of what your house must look like from the outside. And that's kind of how we explore our own galaxy as well. We look at other galaxies, I'll show some examples later, and we kind of explore ours from the inside out. And that tells us that our galaxy actually looks something like this if we were to look at it from the outside. So this is not an actual photograph, it's an artist's rendition. But yeah, this gives you a good idea of what our home galaxy looks like. Here's a slightly bigger view of this. And there's a marker here that says sun. So it's right here. So one of the things I always say is like, hey, look, the sun is right here. It's not in these really cool spiral arms, right? You can see there's one nice spiral arm here. There's another nice spiral arm here. And the sun is actually in between these things, kind of in the cheap part of town, right? So, but yeah, this is our home, and hey, it's a pretty cool home. All right, so we have stars, planets, things called nebulae in our galaxy, and then we also have other galaxies that we can see from our home here. And we'll talk about all these objects more as we go forward. But before we do that, I want to take a short detour and just talk about large numbers, because it's really important to have a sense of large numbers to talk about these astronomy topics. So here's a penny, right? You're all familiar with this object, right? You may have one in your pocket, you may have some rolling around in your car, who knows, right? So 1 penny is something that we can all relate to. And so now here's a bunch of pennies in a bottle. And my question to you is, how many pennies are in that bottle? So yeah, so if you're watching, take a guess, right? And you can throw a number into YouTube chat. How many pennies do you think are in this bottle? And when I ask this kind of question, in front of a live audience, I get a pretty big range of answers, right? Usually I get some answers maybe like 200, or some people say 2,000 or something like that, right? So it varies quite a bit. And that's one of those points that underscores that, yeah, it's hard to know, right? Now, you may be disappointed to find out that I really don't know the answer, but I think it's about 1,500 pennies. And I got there by just doing some math on this bottle. This is not a bottle I've actually had. It's just a picture I found on the internet. It's clip art. So we'll never know exactly how many pennies were in here. But yeah, I think it's about 1,500 based on some calculations I did. But like I said, often the guesses are in the range of like 200 to 2,000, something like that. It's hard to know. It's hard to tell. So one key message here is that it's difficult to estimate or visualize counts of things, especially for very large numbers. Okay, so here's 1,000 pennies. This is something we can wrap our brains around pretty easily, right? This is like a stack that you could imagine sitting right in front of you on your table, right? 1,000 pennies, easy. Here's 100,000 pennies. Okay, we can still manage this too. This is like 2 cubes worth that are like roughly 1 foot on each edge, so like 2 cubic feet worth of pennies. And before we go on, I want to do a little thought exercise with you. Imagine now that you were to get a call from one of your best friends, and your friend's calling you up, and she says, it's like, I need to go out of town for 2 weeks. I really don't want to leave my penny collection unattended. I need your help. Can I please come over, drop off my penny collection so you can look after it while I'm away? And you say, sure, no problem. I can help you out. How many pennies you have? And your friend says, I have 1,000,000 pennies. Okay, where would you store 1,000,000 pennies in your house? Think about that for a second. Where do you think that would fit? Or what if she said, I have 1,000,000,000 pennies to drop off? Where would you put that? Could you even fit that many pennies in your house? So think about that for a moment, and then let's see what it actually turns out to be. So here's 1,000,000 pennies, right? So 1,000,000 pennies is like this wall of pennies next to this cartoon person here. And okay, if you have a big enough bathtub, maybe that would fit in your bathtub. So you can probably take care of 1,000,000 pennies from your friend. 10 million pennies is this big cube right here. This is a pretty respectable stack. And then, yeah, here's 1 billion pennies. So 1 billion pennies is like, 5 school buses worth in terms of volume. I don't think I could fit this in my house. Here's 100 billion pennies. So this is sitting on a football field. Our little cartoon dude is getting pretty small down here, right? And yeah, if you think of a single penny, you can easily lose a single penny in the grass of a football field, right? But 100 billion pennies, that's a pretty big stack. And then to tie this back to the Milky Way galaxy discussion we had earlier, we said we have at least 200 billion stars in the Milky Way. And so that's at least 2 giant cubes of pennies worth in terms of number of stars. Here's 1 trillion pennies, right? This is this big cube next to the Empire State Building. Here's 1 quadrillion pennies, even bigger, and 1 quintillion pennies. You can see that the big buildings are like fading down to almost nothingness down here. So these are big numbers, right? And I want you to keep these in mind as we go through the remainder of this presentation. And actually, even these big numbers won't quite be enough to represent some of the large quantities we'll talk about in our astronomy talk. But yeah, like I said, please keep these in mind. So armed with this, let's talk about distances in space for a moment. So how far is far? So Earth to the Moon is 238,856 miles. Earth to the Sun is about 93 million miles. Earth to the nearest star is about, well, that big number right there. And then Earth to the center of the Milky Way galaxy is that even bigger number. And yeah, notice I'm not even trying to pronounce those numbers, right? Because these numbers are just getting too big to easily handle. So this is very awkward, and we don't like those kinds of numbers in astronomy. So we're going to kind of reframe this in a different way. And to do that, we're going to talk about light. Right, so we see objects in space through the light that they emit, or maybe they reflect, like we see the moon because it reflects light from the sun. Right, so objects out there shine on their own, or they reflect light, and then that light reaches our eyes, and that's how we see those. And it turns out that light travels at a very specific speed. It's exactly 299,792,458 meters per second in a vacuum. But it's also hard to say, so we tend to just abbreviate that or approximate it as 300,000 kilometers per second, or about 186,000 miles per second. So that is the speed of light in a vacuum. And so how long before we see something is the question now. And in a moment, we're going to imagine a mirror on the moon. But before we do that, actually, let's see, I'll just do a little demo with my hand here. So I have here a little laser pointer, and here's my hand. And I can bounce the laser pointer right off my palm. Whoops, where are we? There we are, right? And so the question is, from the moment I turn on the laser pointer until I see the dot on my palm, how much time passes, right? How long does it take for me to push the button and then see the dot? And it feels like it's instantaneous. It feels like there's no time at all. But actually, that's not true. It's just so fast that we don't perceive it, right? Because the laser pointer and my palm are just so close together that I don't really see a delay. But if we now, instead of using my palm, we use the moon, right? It's a different story. So now we're back to imagining a mirror on the moon. And it turns out we don't have to imagine it all that hard because we've put mirrors on the moon. So right here is something that's called the Lunar Ranging Retroreflector. And this is an object that the Apollo 14 mission has put on the moon some time ago. And yeah, we actually use that mirror to bounce lasers off. And yeah, so you can see this mirror sitting here on the lunar surface. This is the moon. And I always wonder about this Ziploc bag that's lying over here. I hope we didn't leave trash up there on the moon. I hope they picked that up before they went home. But anyway, the mirror is up there for sure. And so now we're going to bounce a laser off this mirror. So from the moment I turn the laser on, right, how long will it take until the laser beam has come back down? Okay, and it turns out that will take about 2.5 seconds. So that means the moon is about 1.25 light seconds away. It takes the laser beam 1.25 seconds to get up to the moon, then it bounces off that mirror, and another 1.25 seconds to come back down. So yeah, so now we can express the Earth-Moon distance in terms of light, and it's about 1.25 light seconds. So yeah, so we can express distance in terms of light, and let's talk about just some different examples here. So 1 light second is about 186,000 miles. 1 light minute is about 11 million miles, and 1 light year is about 6 trillion miles. So in 1 year, light will travel 6 trillion miles. Or if you hear somebody refer to a light year, they really mean a distance of 6 trillion miles. All right, now with that, we can talk about our Earth-Moon distance again. We just said that's about 1.25 light seconds. Earth to the Sun turns out to be 8 1/3 light minutes, or I mentioned earlier, we also call this 1 astronomical unit, just as a matter of convenience. Earth to the nearest star is about 4.25 light years. And then Earth at the center of the Milky Way is about 25,000 light years. And that's a lot more manageable than those other really big numbers that we had earlier. So then the distance to our nearest galactic neighbor, which is the Andromeda Galaxy, so that's the nearest house that we can see when we look outside our windows, right, is about 2.5 million light years away. So that's about 2.5 walls of pennies worth in terms of light years. That's the distance. And it turns out that the number of stars in that neighboring galaxy is about 1 trillion. So it's actually bigger or has more stars than our home galaxy here. And yeah, we said 1 trillion is like this giant penny cube here. All right, so now let's take another quick pass through this "You Are Here" story. So again, here's Earth, right? So we saw this before. This is about 8,000 miles across. So if you want to walk all the way around, you're going to walk for 25,000 miles. Here's the solar system. Again, notice that the planets Mercury through Mars are clustered very close to the sun, and then things spread out a lot. Pluto is here. You can see kind of the orbit of Pluto. So the solar system is about 9.3 billion miles across, or about 14 light hours. So it means if I turn my laser on, if I were sitting over here, turn my laser on, it would take about 14 light hours, or excuse me, it would take 14 hours for the light to get to the other side. Okay. Here is our immediate solar interstellar neighborhood. This means this is mostly the bright stars we can see with the naked eye when we look into the night sky, roughly. And so there's a whole bunch of bright stars that are shown here. For example, Vega is a bright star that we can see in the night sky during the summer. And so this solar interstellar neighborhood is about 60 light years in each direction, or about 120 light years across, right? So it takes 120 years for light to go all the way across this size. Milky Way galaxy we talked about before. We said we're about 25,000 light years from the center, and the whole thing is about 100,000 light years across. Here is the local galactic group. So this is the Milky Way galaxy right here with its immediate neighboring galaxies. And over here, this bright patch is the one we talked about a moment ago. This is the Andromeda galaxy, our nearest big neighbor, about 2.5 million light years away. Notice, though, that there are some other bright fuzzies, not nearly as big as Andromeda, but there's something here that's labeled the Large and Small Magellanic Clouds. We call these dwarf galaxies, and if you've ever been to the southern hemisphere at the right time of year, you may have seen them. I visited Australia last year, and I did not get to see them. I was there at the wrong time, unfortunately. But I definitely want to go see these sometimes in the future. So so you can see a whole bunch of cool objects. But the largest, the nearest large galaxy is the Andromeda galaxy, about 2.5 million light years away. And this whole space that's represented here is about 6 million light years across. Then we have something we call the Virgo supercluster. So on the prior slide with our immediate group, this is just a collection of other clusters, and this structure is about 50 million light years in each direction, or 100 million light years across. And then local supercluster, it's another step out. All these little shady, fuzzy things, they're clusters of galaxies, with each galaxy being hundreds of billions of stars. And this is about 1 billion light years in each direction, or 2 billion light years across. A G here is a gigalight year, that means 1 billion. And then finally, this is the observable universe. So here we are sitting in the center, and the observable universe extends about 46 billion light years in each direction. Now, I want to point out one key thing here. I just said we're sitting here in the center, but we're not really the center of the universe. It doesn't matter where you are within the universe. You could be an alien who lives on a planet around, a star that's somewhere up here. If you were looking out from that point, you would still think that you're in the center of the universe. So no matter where you are, you appear to yourself like you are in the center. Okay, so the prior slides were about where we are in space, and I just want to say one really brief sentence or two about where we are in time. The universe overall is about 13.8 billion years old. The Milky Way has been around for almost that long, about 13.5 billion years. Our solar system, the sun and the earth, have been around for about 4.5 billion years, and humanity has been around for about 300,000 years. And in my representation, I really should be drawing a thinner line here, but I cannot draw too thin, because otherwise we wouldn't see it at all. So really it should be thinner, but then it would just tend to disappear. So this gives you kind of a feel for where we are also in time, and we've really only been here for a tiny fraction of the time of the universe. All right, so I think key message here is, you are a citizen of the universe, and the universe is really big. And human history is really only a tiny fraction of all of existence. So it's kind of amazing that we get to sit here and think about all these things, even though we're only a tiny part of all of it. So we can take one moment here and see if any questions have collected. So let me check in with Swami and see if anything has popped up that Swami or I want to address here. Hi, Swami.
Yes, Wolf. So there are a couple of questions.
Okay.
From Teresa Detloff. And one of the questions is just on the slides that you were showing, where you were showing cylindrical, dimensions. And the question is that why are these spaces, especially the solar neighborhood, represented with a cylinder?
With a cylinder? That's a really good question, and I'm not sure I have a good answer for it, because I borrowed those slides from somewhere, and I have in my notes somewhere where they came from. And I understand, yeah, it's like, why is it a cylinder, right? It probably would make more sense to represent them as a sphere, but I think the cylinder just made it a little easier to kind of, represent on a slide, so it's easy to see this three-dimensional structure maybe in a two-dimensional medium, right, projecting it onto a screen or so. So I think that's a really good question. I don't know why the author who made that slide chose it, but I just gave you, I guess, my best guess for that one. So, but yeah, thanks for the question.
Great. And there was another question from Teresa also.
Mm-hmm.
And the question was that earlier you showed a picture of the Earth and the Moon together.
Mm-hmm.
Do you know which craft took that picture?
I do. I can look that up a little bit later if that's okay, right? Maybe at the end, if you're all right with that, I'm happy to provide that information. I do have it. I just don't remember it right now off the top of my head. So, yes. Salmi, can you help me remember that maybe for the end? And we can,
Absolutely.
we can
Absolutely.
answer that.
Yeah.
Yep.
Yeah. There are a couple more questions. Do you want to take them now or later?
Your call. If there's something that makes sense right now, we could probably take one more or so. Sure.
Okay, sure. Anna Choi wants to know, how do people calculate the age of the universe?
Oh boy.
And
Okay,
and,
that's
and,
a lot
and
of,
actually,
yeah.
and actually, a related question from
Mhm.
Mary Ripper is, how did they find out how old the Milky Way and galaxy are? So pretty much same question.
Similar kind of question, right? Okay.
Yes.
Um, okay, so I think, yeah, these are not quickie questions, right? So maybe that's why you were wondering whether we should take them now.
Right.
I'll try to maybe give a really short answer, and that may not be satisfying, in which case we could try to address it a little bit more at the end if that's okay, right? But for example, one way we can kind of figure out how old things are, right? We understand stars pretty well at this point, right? We can look at our own sun, for example, and we know that our sun's been around for about 4.5 billion years, and we expect it to live for about another 4.5 billion years. And we know this based on the size of the sun, how much mass is there, because the sun is mostly made out of hydrogen, and the sun is producing energy by burning hydrogen into helium. And so it starts out as a giant ball of hydrogen. We know how much energy is coming out of the sun because we see it and feel it every day. So we know how quickly the sun is burning through its fuel. And based on that, we have an idea of how long the sun has been around and how much longer it will be here. And we can look at that same kind of thing for other stars as well, right? We know that there are stars out there based on their size and how much energy they put out. We know that some stars, turns out, live for, let's say, 100 million years. Other stars could live for up to 1 trillion years, longer than the universe has been around. But so that's one mechanism we can use to kind of, date things, if that makes sense. And then there are also other mechanisms like the expansion of the universe, right, that is also used to help date the universe overall. Maybe I'll leave it here for the moment because otherwise we would go off on a big tangent. But actually, it's a really good question. I like your question.
Yep. Okay.
Okay.
That's all for now. Yeah.
Okay, great. Thank you very much. Okay, let's move on here. So if we look into space, right? We can just look up. I want to be clear here. You can do a lot just by looking up into space with the naked eye, right? Astronomy, we tend to think of telescopes, and telescopes are cool, and I have probably way too many in my garage. But you can actually see a lot of cool stuff just by looking up, especially in the dark side with your unaided eye. And so here's that picture that I flashed earlier. Yeah, so here's the winter sky. It turns out there's the constellation of Orion. And this picture was from an event at Pinnacles National Park that we did a little while ago. So yeah, you can just see a lot, by looking up with your own eyeballs, right? So don't discount those. Or you could use binoculars, right? So binoculars are also a great tool to look at the night sky. So if you have some, you can bring them out, look at the night sky, and you'll be amazed how many more stars you see than you would otherwise notice with the naked eye. Okay, but you're probably here listening to astronomy stuff to learn about telescopes, right? So let's talk about that a little bit here. Okay, so why do we use telescopes at all? And usually I kind of open this question up to the audience when I do this in front of a live group, and I can kind of, I guess, toss the question out to the YouTube audience as well, and you can type an answer into the chat if you like. So why do we use telescopes? And I typically get, one of two answers. A common answer is to magnify, and that's true. Telescopes absolutely magnify stuff, but it's actually not the most important aspect. So it turns out the other important aspect is to collect light. It's to make faint objects brighter. And so the problem is this, right? So when we look at the night sky, or anything really, with our eyeballs, right, light is entering through the pupil, right, the little hole that we have in the middle of our eyeball. And the pupil here changes size. You've all seen this, right? In bright light, your pupil might be like 2 millimeters or about 3/32 of an inch. And in darkness, it'll expand to about 8 millimeters. And as you get older, this gets creakier, and then, it gets harder to make the pupil really big. So our night vision will tend to diminish as we get older. So these things kind of vary with person and age, but this is what happens pretty much for all of us. So, that little hole is not a big hole to collect light. So we need like a light funnel. And the analogy I can illustrate here is, imagine you're really thirsty, right? You're thirsty, you need something to drink, but you have no water fountain or no water bottle nearby. How will you get some water? Well, it turns out it's raining outside, right? You could go outside and you could just stand in the rain with your mouth open, right? And you would collect raindrops. But it would take you a really long time, right, to quench your thirst, because most of the raindrops are going to miss your face, are going to miss your mouth, right? And only a few will collect in your mouth. So you can do much better if you were to have a funnel, right? If you put a funnel on your mouth, right, now you're collecting a lot more of the raindrops, right? And they would get then, funneled into your mouth, and you could quench your thirst much more quickly. So it turns out we can do the exact same thing with light. So binoculars are light funnels already, right? They magnify things, but they're also light funnels, because this right here is the opening of the funnel. This is where the light enters, and then it gets squeezed down until it finally can get pushed into your pupil. And binoculars have what we call an aperture, or an opening. This is the funnel opening of maybe 50 millimeters or 100 millimeters. There's a whole bunch of possible sizes depending on the kind of binoculars you have. For astronomy, we tend to be in this range of 50 to 100 millimeter aperture opening. And telescopes then are also light funnels, right? So here, again, it's the opening. This is an example of about a 100 millimeter telescope, or about 4 inches. Light comes in, gets squeezed down, and then pushed into your pupil. So so basically these things are light funnels, just like we use the funnel to drink out in the rain. So here's a bunch of telescopes, right? If you were to join us at a star party out on the sidewalk in Hoagie Park, or at another dark site, which I hope you'll be able to do at some point in the not too distant future, you would see a bunch of different telescopes out there operated by different SJA members. Okay, but the key point here is aperture diameter is the aspect, or the attribute that measures how much light we can collect, right? So the size of this opening, the bigger the opening, the better. And magnification is also a thing, but it's actually not the most important attribute. Turns out that for all these telescopes, we'll end up using about the same magnification, but the key difference is that the ones with the bigger opening can collect more light and see fainter objects. So now, let's say you were to buy a telescope, and you can have the one on the left or you can have the one on the right. Which one would you buy? And notice that the one on the right has a little, person down here for reference and size. And when I bought a telescope, I actually bought the one on the left because I didn't know how to fit the one on the right in my car. And it turns out the one on the right is a representation of the Hubble Space Telescope. So that's actually a replica of what's floating up in outer space. So let's talk about a little bit how this works, right? So amateur telescopes come in a few different varieties. There are things called refractors. They use lenses, and there are other types of telescopes called reflectors, and they use mirrors. And we already talked about the aperture ranges a little bit, maybe 100 millimeters to maybe 300 millimeters, 4 inches to 12 inches. And there are things outside this range. This is just to give you an idea, right? There are some reflectors in the amateur astronomy world that are, let's say, up to 30 inches of aperture, but those are pretty big, typically stationary scopes. But all of these telescopes, regardless of how large the aperture is, have one common problem, is that they need to look through the atmosphere, right? Now, the Hubble Space Telescope does not have this problem, right? It can look right out into space. It does not have to look through the air. Now, why is this a big deal, right? Imagine for a moment, we can think back to our pennies earlier. You have a penny in your hand, and you throw a penny, let's say, into a wishing well, right? So the penny goes below the water, and the water surface ripples. And as the water surface ripples, right, the image of the penny that's now under the water is wobbly, right? It's not steady. And it turns out our atmosphere wobbles kind of like the water wobbles or ripples, right? So when we look at objects through our atmosphere, they appear distorted, just like the penny appears distorted when it's under the water. So we have to struggle with that when we look through the atmosphere, but the Hubble Space Telescope does not have that problem because it's above the atmosphere. Now, the largest ground-based telescopes that we have are all pretty much mirror-based reflectors. Here's a picture of the Keck telescopes in Hawaii. It's about a 10-meter mirror each. Here's a picture of that mirror. Notice the mirror is interestingly built out of all these hexagons. It's kind of cool. And I'll just kind of throw this out there. Hey, if you work at one of these telescopes, you get to shoot lasers off into space, like in this representation. And if you wonder why we do that, you can maybe ask a question in the YouTube chat. But yeah, so these guys still need to look through the atmosphere. Now, we said earlier that larger aperture collects more light. Okay, that's our larger funnel, right? Bigger light funnel. But there's another way we can collect more light, is kind of by looking longer. And that maybe sounds funny at first because it's not something we can actually do with our eyes, but we can do it with camera equipment, right? Our eyes kind of see continuously, but with cameras, I can choose how much light I collect. If any of you are photographers, you know exactly what I'm talking about. It's the shutter speed, right? It's the exposure time. So you could choose to open the camera shutter for just a fraction of a second, or you could open it for a second, a minute, or hours if you want, right? And the longer it's open, the more light you will collect. Okay, and yes, you can even do this with amateur telescopes. Here's an example of a camera, strapped to the back of this amateur telescope. Okay, and so space and professional ground-based telescopes all use cameras. These days, there's not really anybody at the eyepiece anymore looking through. For all the professional science that's out there, these are all done with imaging equipment. Okay, and that's also what the Hubble Space Telescope does, right? So the Hubble Space Telescope has a 2.4 meter aperture or 2.4 meter mirror, and that's actually not even that big, right? That's just a little bit bigger than I am tall, it turns out. But it has no atmosphere to look through, like we said earlier, right? And it can take long exposure images with the camera equipment it has on board. And so now we'll look at a really quick teaser, right? So if we look off into space, we can see all kinds of cool objects, right? So here is a picture of the sun, probably in a way that you're not usually seeing it. If you want to learn more about the sun looking like this, you can join us for one of our solar astronomy events that we typically have the first Sunday of the month. Image of the moon, you're all familiar with the moon. But then here are some other objects, right, from within our solar system. Bottom left, of course, Jupiter. Top right is Saturn, beautiful planet. Bottom right is Mars, and the top left is a little bit more tricky. It turns out that's Pluto, an image that was returned from the New Horizons mission just a few years ago. Until that mission, we had only just seen Pluto as kind of a fuzzy blob. Here are collections of star clusters that we can see with with telescopes like the Hubble Space Telescope, or even from the ground. And right now, don't worry too much about the details here, but we can just look for high-level patterns for a moment, right? I think you can all agree that the thing we see at the top left and bottom right, they appear to be like the same kind of thing, right? And even the bottom left and top right are actually the same kind of thing. Here we see things called nebulae, and again, for now, just notice the similarities, right? These two things up here in the top left seem to be similar, and then maybe these two guys look similar, right? So we'll visit these again, and we'll talk a little more about what these are. For the moment, though, you can just kind of enjoy that they look pretty cool, right? And here are galaxies. We visited this one once before. There's a couple other galaxies that we can see looking out into space, and I think they're also just very beautiful. So all this stuff that we see looks very colorful here, right? And so that's why I want to take a moment and talk about color in space, okay? So, and this is going to be disappointing perhaps for a moment here, right? So brace yourself. So, I showed you this cool picture of the Andromeda Galaxy, and it looks nice and colorful. Now, if you look at it through a ground-based amateur scope, it will probably look more like this thing you see over here on the right. Actually, let me go to the next slide and illustrate that a little bit better. So here's that nice big picture again. But on a really good night, under good conditions, this is what you might see through a ground-based amateur telescope. Notice there's no color here, but you do see some structure. As the sky gets brighter or the conditions degrade, right, maybe you'll see this, or on a really not so good night, right, maybe you'll just see kind of a fuzzy blob in the center here. Okay, but most of the time you'll probably get something like this. So there's no color here, which is kind of a bummer, right? So I want to prepare you for when you look through an amateur telescope for the first time. Don't expect to see, the gloriously colorful pictures that Hubble shows you. You will not. But I still think that looking through a telescope directly is a very visceral experience. It's very cool. So on one hand, I keep in mind the cool pictures from Hubble. On the other hand, I see something with my own eyes. My eye is collecting photons, light particles that have come to me maybe over millions of years, and that's pretty cool. And you can kind of do these things together. They're nicely complementary. But so what about this color, though, right? I just told you you're not going to see it, but it still means something, right? So what's going on here? Well, so one thing is that color is real. So you may see color in these images. That's absolutely real. but it's invisible to the eye. So here is something called the Horsehead Nebula, which is also a pretty well-known image because it looks a little like a horse. And the red glow you see is largely from hydrogen gas. It turns out hydrogen gas glows in the red, but our eyes are not very sensitive to red light, so we cannot see that color when it's too faint in the night sky. But cameras, like we said earlier, right, can actually reveal this. So if I take long exposures, yep, I can see that red stuff pop out. Okay. Now, there's also something called false color, and I want to be really clear that false color is not fake color, right? So false color reveals details we otherwise cannot visualize, and there's a couple different ways we use this. One is different chemical elements may be represented by different colors. So we may have determined that a certain structure is, let's say, an oxygen cloud or a hydrogen cloud or something like that, and we may choose to color those different chemicals differently so we can easily see what's what. So that would be one example of using false color. Another example is that light outside the range that our eyes can detect may be translated into the visible range, and that's also false color. So down here again is our picture of the Andromeda Galaxy we've seen before. If we look at that with instruments, we can look at it in the infrared range of the spectrum. This is light our eyes cannot see, but we have instruments to see it. And then I translate what my instruments see into the visible. I make it appear red, so it's a false color, right? But otherwise, I couldn't see it at all, right? So here, yeah, this is a representation of what our instruments can see in the, I'm sorry, did I say UV before? I'm sorry, infrared light. This should be the infrared light. On the right side is the UV image. This is the ultraviolet light. So neither of the ones on the outside we can see, but we can use, false color techniques to make them visible. Here's another cool picture. This is the Eagle Nebula, what's called the Pillars of Creation, and just another example of how we use devices, right? Use our technology to make certain things visible. In visible light, it looks like it is on the left, and that's a cool picture all by itself. But on the right side, look at how many more stars you see there, right? And we can reveal those by looking at this patch of space using infrared light technology, right? Using infrared light detectors, and that allows us to see through what astronomers call dust. There's a bunch of dust here that blocks light, but turns out the IR detectors can see through that dust and see all these stars, which is pretty amazing. So yeah, so color is key, right? Different wavelengths, invisible colors, colors that might be invisible to our eyes, allow us to learn a lot more about what's out there. And also I say that color reveals the building blocks and structure of the universe. And we'll talk about that a little bit more. But before we do that, let me take another moment here and see if any new questions have collected that we can quickly address.
No further question, Wolf. Your description about colors and why we cannot see colors was very helpful, because that was playing on some people's minds.
Oh, cool. All right. Well, thanks. Okay. So if you have no questions now, great. I hope that's not because you guys fell asleep. Please stay with me because we got a bunch more to go through. So let's keep going. So, all right. Nature's Lego blocks. All right. So here, you're probably all familiar with Lego blocks, right? So, I had Lego blocks as a kid. You probably did too. And if you have kids, maybe you stepped on a Lego block not that long ago. And the key thing here is that, you can build almost a countless number of objects from different types of Lego blocks, right? These are some of the basic building blocks. And if you have enough of them, you can just build almost anything. And let me kind of maybe give you a flashback to high school, right? Do you remember this thing? This is the periodic table of elements. Depending on how you felt about this in high school, maybe put you to sleep or made you panic. I think I was a little bit more like Homer up here. This kind of scared me way back when. But it's actually not so bad, because really this thing is just nature's Lego blocks, and some of these. For example, here, this one is gold. You probably have some in your teeth. I know I do. Right here is carbon. Carbon is in the pencil. If you use the pencil today, you use carbon, right? And diamonds, that you may have in some jewelry are also carbon. If you take a deep breath, oxygen, it's right here. This is one of nature's Lego blocks, and you use it to breathe and stay alive. Helium, this is what goes into party balloons. And here's calcium, which is a metal, right? But usually you probably think of it as something that's in your bones. So yes, you actually have metal in your bones, which is kind of cool. And then we can take different of these Lego blocks and put them together. You almost certainly ate some salt today. It's sodium chloride, right? So here's another really familiar material. So all this stuff is built out of nature's Lego blocks. And I want to focus on these three for the moment: carbon, oxygen, and hydrogen, right? And so carbon is like one that has 4 little nubs on the Lego block. It can snap together with 4 other things, oxygen with 2 other things, and hydrogen with like 1 other thing, right? It's these guys on the periodic table. And yeah, so let's ask the question, if we use HCNO, what can we build? Well, actually just HO by itself creates water. You all know this, right? H2O, you've heard this, and again, you've had this today, right? You've had some water to drink. It's one of our most important chemicals. Yep, and H2O, like we said, you got the oxygen. It can snap together with two things. And it turns out it's snapping together with, two hydrogens here. So this is water that you've had to drink today. But now if we put the carbon back in the mix, right? If we say, what can we build out of HCO? It turns out we can build us almost entirely. So the stuff in you and me is almost entirely these three things. If I were to take any one of you and I were to take you apart, building block by building block, atom by atom, and I were to make three piles. I would make a hydrogen pile, an oxygen pile, and a carbon pile. Those piles would be pretty big because that's almost all that you're made of, right? So 63% of your atoms are hydrogen, 24 oxygen, and 12 carbon. And there's still like 1% of other stuff, right? Now this is by atom count. Hydrogen is really light because it's the simplest one of these Lego blocks. If we do it by weight, turns out these three things account for just 93% of you, but that's still a lot. So now, if you wanted to go build a human, let's say you want to make another human being and you're not going to do it the old-fashioned way. Instead, you want to go to the store and just buy some supplies and go assemble this person in your garage. What are the top 10 things you have to buy? And it turns out it's these. So we already talked about hydrogen, carbon, and oxygen, but you would also need these other guys that are highlighted here, like sodium, magnesium, and potassium and such, right? So it turns out that those are basically you. So I find this kind of fascinating, right? So on one hand, of course, you and I are pretty complex beings, pretty complex entities. But at the same time, we're built out of really simple stuff, right? So on one end, our chemistry is actually very simple. On the other end, it's actually very complex. And it's amazing how you can look at it from both of these perspectives. So these are all of nature's Lego blocks, including some that we have made artificially in the lab. And key message here is that everything and everyone you've ever seen, you've ever touched, is made from these building blocks. Everything. Okay. And just kind of to stitch this together, earlier we talked about how old the universe is. Well, we said 13.8 billion years ago. The young universe had only hydrogen and some helium, right? And I said earlier that we can use stars to help us, for example, date how old the universe is. Because we know that the young universe had only hydrogen in it and maybe a little bit of helium. That hydrogen collapsed into stars. Those stars ignited and then burned their hydrogen fuel into helium and other things. And ultimately, that produces all of the items on the periodic table, all of nature's Lego blocks. I realize I've skipped a lot of steps here, but this is what happens. All right. And so another key thing here is that when any of these things, any of these Lego blocks, any of these elements is excited or energized, it emits a very unique set of colors, right? So I think of that as a barcode. Imagine you go to the store and you buy a bunch of stuff and you go scan out on the checkout line, right? Boop, boop, it runs across the computer reads the item and the price. So the barcode is a unique identifier for the item you bought, and it turns out this is very much the same. So here at the top is the full visible spectrum from violet through red. This is what you see when you see a rainbow in the night sky. And hydrogen gas, for example, if we energize hydrogen gas, it will glow with these very four specific colors within the range of the rainbow colors, right? So these are the four colors we get from hydrogen. And then these four colors are the ones that are kind of compressed down here. And it turns out hydrogen gas also glows with a bunch of colors that we cannot see with our eyes, right? Like we said earlier, there's a bunch of colors we can't see, but instruments can see them for us. And so yeah, it turns out this is like the complete barcode of hydrogen down here that we can see, including with instruments. Here are some other examples: helium, lithium, oxygen, for example, carbon, right? You can see that each one of these has a unique pattern, a unique barcode. So the amazing thing here is that stuff can be immensely far away, right? So we can see light from objects in the night sky that is farther away than we could ever possibly reach, right? We'll never get there, but we can still tell what it's made of because we can analyze the light and we can read that barcode. So I think that's pretty amazing and pretty cool. And with that, let's take a closer look at objects we see in space. We'll revisit some of the things that we quickly introduced earlier. So if we go back to our own solar system, we have, well, we used to consider it 9 planets, and then we kind of demoted Pluto to a dwarf planet, which doesn't make it any less cool. It just has a different classification. But now we say, yeah, there are 8 planets, 4 rocky ones, up to Mars, and then these guys over here are the gas balls. Now, and a question we can ask, are there planets elsewhere? And when I was a kid, we had no idea. When I was little, we only had our own solar system and our own planets as examples. But we've actually been looking a lot, and you know, so 30 years ago, we had no idea. Now we found over 4,000 exoplanets. And notice that I crossed something out here, right? When I first made this presentation, which is not that long ago, we had found about 2,000 exoplanets. But so I had to update this. Now it's about 4,000 exoplanets. And that's only in a pretty tiny patch of sky. And over on the right is actually an image of a couple exoplanets. So there's a star in the middle that we've blocked out. We put something in front of it so that it wouldn't be so bright as to wash out the image. And then through infrared light imaging, we can see that there are planets around. So this is pretty amazing. We can actually image planets around other stars. Whereas, again, when I was a kid, we didn't even know if any existed. Moons. Some planets have moons. So, of course, we have our moon, right? Other planets have a lot more. Moons are distinct individual worlds. And for Jupiter, we know that there are, again, here I had to make an update. It was 69 when I first made these slides. And hey, now we can count 79 moons for Jupiter. And there are 4 big ones. We call these the Galilean moons. These are the ones that Galileo also saw. And you can see them pretty easily through a telescope or even with big binoculars. And this picture here on the left, this is not how the moons would really appear in terms of arrangement. But this shows you that each of these has a very unique surface structure and color, right? So they're all different. They all have their own geology, their own chemical composition, and geologic activity. So these are all uniquely different. For example, this guy here, this is Europa. So we think that there's a giant internal ocean, right, covered by giant ice sheets. And there are some ideas that, hey, maybe there's some life in that ocean. We don't know. Now, we just talked about, moons and planets, but we wouldn't see any of this stuff if it weren't for stars. Stars are the things that light up the universe. And, our sun is a star, like we said at the beginning. This is not something we've always known. Some stars are really big, and some existing stars are almost as old as the universe, like I mentioned earlier. And it turns out it's actually the small ones, which may strike you as counterintuitive. It certainly does me. Now, a star's color indicates its temperature. We can look into the night sky, and you can do this, just looking through a ground-based telescope pretty easily. You can see stars with different colors, and right there you can do a little bit of science. Turns out that the red stars are a little bit cooler, and the whiter, bluer stars are, relatively speaking, hotter. So yeah, that's kind of cool. So next time you look at stars through a telescope, you can do some science right there. Now, who's this guy? You'll probably all recognize this person, right? One of the most famous scientists who's lived in recent history. Of course, it's Albert Einstein, here with probably one of the most famous physics equations, E equals mc squared. And I just want to take a moment here to relate this to our everyday lives. We hear this thing and it's like, well, sounds cool. What does it mean? I don't know. Well, it turns out it actually means something to us every single day. This equation describes how mass and energy are related. So m here is mass, as in a kilogram or something like that. And how does that relate to energy? It turns out mass and energy can be converted from one to the other. And it is done, or the relationship is described through this expression here, where c squared is the speed of light squared. So, and this is a huge, huge number, which implies that a little bit of mass can give you a lot of energy. And it turns out that's what the sun does, and all the other stars do, right? So they take hydrogen gas, and in the core of the sun, the hydrogen gas is smashed together so tightly that a process called nuclear fusion converts it to helium, the next more complex Lego block, right, on their periodic table. And during that process, energy comes out because, and I'm going to fudge the terms here a little bit, but for sake of illustration, let's say we weigh that, the couple of hydrogen atoms that we start out with. We weigh them and they have a certain weight or a certain mass. Then we do the fusion thing, right? And then the helium comes out and we weigh the helium. It turns out that the helium weighs a little bit less than the hydrogen we started with. So we lost some mass. Where did it go? Well, it turns out that mass was converted to energy. And our sun converts about 5 million tons of mass to energy every second. This sounds like a huge number, but the sun is really big. It hardly notices this, right? Now, also, this energy number may not be all that meaningful to you, because how much is 3.8 times 10 to the 26 joules? I don't know. Turns out it's about this many Twix bars, right? So I've converted this to Twix bars for you, just to give you some idea. If you ate this many Twix bars every second, you would be consuming as much energy as the sun puts out every second. Why Twix? Because I like Twix. You can substitute your own candy bar if you like. But yeah, so every day the sun is performing this mass energy conversion, and that's in fact what powers our lives. So E equals mc squared is very intimately related to our lives every day. And so the stars, like our sun, is huge, right? So here's a representation of the sizes. Earth is a little dot down here, and the sun is much bigger. Okay, and in fact, let's do some other sizes right here. So here is Mercury, Mars, Venus, Earth. Okay, now we shrunk the Earth down. Here are other planets: Neptune, Uranus, Saturn, and Jupiter. Now we shrink Jupiter down here. It becomes this little ball. Here's a star called Wolf 359. No relation. Here's the sun. Here's Sirius. Now we shrink down Sirius. Look, Sirius became this little dot down here. Here are some more stars, going all the way up to Aldebaran. And actually Arcturus, this star, is a star you can see in the night sky probably right now if you want to go outside. It's up there. And then here, now we shrink this guy down. And look where it went, right? And that gets us up to Betelgeuse, an enormous star. If we were to put Betelgeuse where the sun is, we would be inside it. Jupiter, I think, would be inside it. And then finally, we go all the way up to this guy, which is the largest star that we have found. And by this time, the Earth has become, an unrecognizable, tiny, tiny, tiny pixel here. So things can get really, really big out there in space. And and it turns out stars like to hang out with friends. There are things called open clusters. An open cluster is a bunch of sibling stars that were born from the same hydrogen gas cloud. So hydrogen gas started out, stars formed, and they usually form in a group. You'll find hundreds or thousands of stars in this loose arrangement, and there are many of these open clusters that exist within our galaxy. Then there are also structures called globular clusters. They were formed through a different mechanism, and they are a tight spherical globe-like arrangement of stars. And typically there are like 100,000 of stars, and they're often very old, almost as old as the universe. And we know of about 150 of them that orbit our galaxy. They're kind of companions to the Milky Way, and I think they're very beautiful. So these two are examples of open clusters. This is called the Pleiades, probably something you may have heard of. And we saw this one earlier. There's something called the double cluster, is one of my favorite objects. And then here, these are globular clusters. I just think these are beautiful. So each one of these globular clusters, a few 100,000 stars, really densely packed. Turns out we don't really think there are planetary systems in these clusters. But if we were to imagine that we were there, the night sky would be full of stars. It would be, I think, 20 times brighter than a full moon night is here today. So if we lived inside here, our nights would be nothing like the nights that we experience today. They would be way, way brighter. Okay, then we have things called nebulae. So a nebula is basically a fuzzy thing in space, right? When astronomy was young, we looked up there and said, hey, there's a fuzzy. And we said it's a nebula. But since those early fuzzy days, right, we've learned a lot more about what these things really are. And we can describe things called emission nebula. An emission nebula is a gas cloud that's somehow energized and it's glowing, right? So it's actually emitting light. There can also be reflection nebulae. That can be, again, a gas cloud or dust that's reflecting light. So there could be a star here. Here's this cloud, right? And light bounces off, and then we see that reflected light. And the gas in these nebulae is often less dense than the best vacuum on Earth. When you see nebulae depicted in sci-fi movies, it's often, like this really dense fog, and the spaceship flies in, and there are rocks all over the place. In reality, these things are hugely diffuse, right? And you might not even know that you're inside it. You wouldn't necessarily, obviously, notice it. Then you also have these things called absorption nebulae. So these are dark structures, and that would be something that blocks light. So maybe there's a light source here, and there is a cloud in between the light source and where we are, and so we see then that nebula as a dark patch. And these things can be huge, up to thousands of light years across, right? And if we think about what these things actually represent, it turns out that they are nebulae that are star-forming nebula. So we call these stellar nurseries, newly formed stars, energized surrounding gas. So you have the hydrogen gas that formed the stars. The stars now radiate energy into space, and they call the parent gas to glow. And these things will ultimately turn into open clusters, right? We said earlier, open clusters are sibling stars. So you form the stars in these nebulae, and eventually they become open clusters. On the other end, these nebulae can also be star remnants. So you could have a star that has died. And there are two basic classes, something called a planetary nebula. Terrible name. Ignore the word planet in it. It's confusing, but don't worry about it. Just go with it. And turns out medium-sized stars like our own sun form these things called planetary nebulae. And then there are things called supernova remnants, much bigger stars. That's where something blows up and blasts a whole bunch of material off into space. And these dead stars, when they shed their material off into space, actually create the material that planets are made of and possibly life. So our sun, and we are here because other stars died in this neighborhood of the galaxy, right, and created the other building blocks on the periodic table. So we are here because other stars lived and died in this neighborhood of space, creating all this other stuff that we're built from. So here are a couple examples of stellar nurseries. The one on the top is the Orion Nebula in the winter sky. It's a very nice object, and the one on the bottom is visible in the summer sky. It'll be a little more visible a little later this summer, but yeah, this is a nice object called the Lagoon Nebula. These guys at the top, these are planetary nebulae. So here there is a tiny, now inert core of a star in the center, and the bubble is material that the star has kind of poofed out into space. And the bottom right is a remnant of a supernova explosion. So there, a star actually went kablooey, right, and blew material off into space even more violently. And here are a couple more pictures of just supernova remnants. I just think these are beautiful. These are giant bubbles in space, material that may in the future get somehow used by the natural processes out there to make new planetary systems and maybe seed life somewhere else, who knows. And then, yeah, we mentioned galaxies earlier. I say here that galaxies are the engines for planet and solar system formation because, yeah, galaxies are the places where stars live and die. And as stars live and die, they create all these other materials, right, that we're made of as well. And yeah, Andromeda is our nearest neighbor, about 2.5 million light years away, about 1 trillion stars. And a new fact here is that we will actually merge with the Andromeda galaxy in about 4.5 billion years. So we are actually approaching each other. The Andromeda galaxy is getting a little bit bigger in the night sky every day. And here's an example of how big it is currently. Now, you would never see this arrangement. You would never see the moon next to the Andromeda galaxy like this. They're not really in the same area of the sky. But just to compare the sizes, if you could see the Andromeda galaxy fully with your naked eye, yeah, it's this big in the night sky. It's like 6 full moons across. Now, the outer ranges here are really a little too faint to easily see, right? Even with a telescope, we tend to see the bright core. But yeah, next time you see it, keep in mind, it's really that big in the night sky. We just cannot easily see all of it. So I find that kind of amazing. Some more pictures of galaxies. Again, just beautiful, right? These are all flattish, spirally structures. Similar to our own Milky Way, but in some ways also different. You can see that each looks unique, but they're all the same type of thing. Here's a couple more pictures. Now here, like I said earlier, we take some of these pictures by looking longer, right? By imaging over long periods of time. And here light was collected for a total of almost 35 hours, right? So that's not going to happen quickly, but it does reveal, beautiful pictures. So here is that same picture again from the prior slide. So you'll never see that when you come to a star party looking through the telescope. But on the right side is a picture that I took at Pinnacles. And here, if you're in a dark side, you can actually see something like this through a telescope. So, you can still see some of the structure in this galaxy. And this is a galaxy we're seeing kind of edge on. So a bunch we see face on. This one is edge on. That's why it looks like a stripe, right? But the key thing here is that, yeah, we'll never see this through a telescope here because this was done with complex imaging. But under really good conditions, yeah, you can see this through a telescope, and still a lot of detail to be seen. Now, galaxies, the universe is full of them, right? So here's a picture called the Hubble Deep Field. Here we have the Hubble Space Telescope stare into a seemingly dark patch of sky, and that patch of sky was small. It's like 10% of the moon's diameter. It's like this little rectangle here. So the Hubble Space Telescope stared into this tiny patch, and boom, it found all these bright spots, and these are all galaxies. So within this image, like what's the brightest galaxy? I think it's this one down here, right? So right here, yeah, look at this. This again looks like this nice spirally galaxy structure like we saw on the prior slides. It's just this guy is really far away. Here's just another version of that same picture. I just think this is kind of mind-blowing. So if we look at this and we estimate how many stars we think are out there, it's a lot. 10 to the 29 or 100 octillion stars in the universe. That's like 100 trillion giant penny cubes. Pretty amazing. And yeah, with that, let's kind of wrap up. So thanks for sticking with us this far. When you look out, enjoy your views of the night skies and the cosmos. Just look up. You can see a lot. And as you look up, think beyond what you see. The light you see has been traveling for a long time. Even just the sunlight tomorrow will have been on its way for 8 minutes before you see it. But some of the nighttime structures, can be thousands to tens of millions of years away, light years away. And space is really big, as well as the objects within it. And think about how each object fits into the cosmic history, right? We see stellar nurseries, we see places where stars have died, and what does that say about our history and future? And also, hey, what does it say about the chances of other life in the universe? And just to kind of review this, right? So we said the universe started out with hydrogen gas, formed stars, galaxies, are big collections of stars. Within those galaxies, stars die, like in the supernova. This stuff makes all of the elements on the periodic table, and it turns out that the Earth and us is made from this stuff. And, there's no reason to think, I think, that this is somehow unique to our part of the universe. We just have only one example so far. We've only met ourselves, but you can decide for yourself whether you think there might be life elsewhere out there. Here's a really nice quote from Carl Sagan, who was an astronomer and science communicator from a little while back. And he wrote, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." I think this is a very poetic quote. All right, if you like this stuff, what would you do next? So normally we would have, a bunch of star parties to offer you that would be outside. We can't do that now, but please, when we return to a somewhat normal life, maybe you can join us for star parties in Hoagie Park, as well as solar observing, although we do solar observing now online a little bit. We also usually have star parties at a place called RCDO. It's a nice dark sky site. Can't do that right now either, but we are offering our online armchair star parties, right, that you can witness from your home. And ordinarily we also go out to Pinnacles National Park, which is a nice place. Like I said, we do outreach sessions for schools. Of course, schools will have to reopen for that to really work, but keep that in mind. We have telescope fix-it sessions normally, where you can bring your scope and we can help you take care of that and get that working. We have science speakers, and we still do that, so we do those online. We had a nice talk about Mars just last Saturday. So look for those. And we have our Astro Imaging Special Interest Group that's operating right now during the coronavirus time. And we have our library and loaner telescope programs. That's a little bit on hold right now. And then we have lots of other events, for club members specifically. And a reminder, if you want to spend the price of a pizza, hey, you could join the SJA as a formal member. If you're interested in doing something for SJA, let us know, right? If you're interested in helping out, or in learning more science yourself and then promoting astronomy and science in general, we could definitely use your help in technical and non-technical areas. Don't worry if you don't feel ready, just let us know if you want to contribute and we can help you get ready. So some resources, there's something called the Astronomy Picture of the Day. They have cool stuff. You could check that out. There's something called Crash Course Astronomy on YouTube. You can get nice little 10-minute tutorials on different aspects of astronomy. Some podcasts that are good. And there are also some other resources here. There's a nice free planetarium app called Stellarium. You could check that out. This works on Linux and Mac and Windows. And you can also, of course, get these things for your tablets. And then you can get these kinds of sky maps. We talk about how these work a little bit in the Armchair Star Party. There's something called the Chabot Space and Science Center you may want to check out once they open again. And again, there's some other resources here. I'm going to collect all these links and put them on a page at the SJA site sometime soon so that it's easy for you to get this stuff. I realize you can't all remember these right now. I'll just finish off by saying that, science is our tool for unlocking the universe. There's a lot of stuff we know, and there's a bunch of stuff we don't know yet. We didn't talk about dark matter, but you've probably heard this term. Dark matter is a thing we don't really understand yet, right? But I'm pretty sure that as we work on this stuff, we convert more and more from this side to that side. But, especially for young people out there, a lot remains to be discovered, right? And you can help. So, if you want to become a physicist, astronomer, or other scientist, hey, there's a lot to be learned, cool things to be known. So with that, thank you. My name is Wolf. If you want to send me a note, you can send it here. Other than that, this was stuff in space. I hope you got something out of the last hour. These are the kind of objects we visited in space. If, counter expectation, you actually look through a telescope and see this stuff in space, let me know, because I want to see it too. This would be kind of surprising and amazing. Okay. So thanks. I guess let's take another moment to see if questions have collected. And also, let me throw out a question for you, I guess, right? You can maybe answer that for me in the chat. In today's presentation, is there anything that you found most interesting or that was most surprising? So I'd be curious to hear about that. But we can handle your questions first. Hey, Swami, what's happened in the YouTube chat?
Well, the YouTube chat has been very, very active. We have had lots of interesting conversations going
Cool.
on.
Excellent. Yeah.
One of them centered around some of the cat meows that we heard coming on the stream.
Yes,
And
yeah.
then
That
there was
really, there's a cat that owns the house, and he just lets me live here. And sometimes he makes announcements. So yes,
that's
he contributes.
that's how cats are. But at the same time, we could also hear some chirping sound coming, so we weren't sure if there was a bird there also, or if it was coming from one of our equipment, audio equipment, maybe.
I think yes, that was a bird outside. That there's a bird that's been visiting. I think it's always the same bird for like the last 5 days. There's a bird
Uh-huh.
that comes and sits on the tree outside and drives my cat nuts, and then the same bird also sits on the deck outside and drives my cat nuts. So
Okay.
yeah, I think this bird is either just wants to make friends or is just taunting, likes taunting
Okay, so
humans.
it was a real bird, not
It's a
one of
real
our
bird. Yes.
equipment malfunctioning here.
Yeah.
All right, so there are a couple of astronomy related questions
Okay.
also. Anna Choi wants to know, and I'm going to paraphrase the question a little bit, that does the sun emit the same energy or does it have the same temperature evenly, or are some spots hotter than the others?
Okay, so I think the question is asking if I look at the quote unquote surface of the sun. Now the sun does not have a solid surface, right? But if we talk about the surface of the sun, I think the question is if I look at different spots on that surface, are all those spots the same temperature? You think that's what it's asking, Swami?
Yes, yes.
Yes. Okay.
Mhm.
I think the answer is no. There's variation. Different stars, well, all stars have some variation in terms of the energy output over time and also within, across their surfaces, and our sun does that also. We can talk about this a lot more in the solar Sunday event if you want to join us for that in the future. The short answer now is that, yeah, the sun can actually be quite active. It goes through an 11-year cycle. Right now, we're at a phrase called the solar minimum, where the sun is actually relatively uniform. It's relatively smooth. There's not a lot of variation across its outer layers, across its surface. But near a solar maximum, which we'll get back to in about 5-ish years or so, then there's going to be a lot of variation, and different spots will be differently active on the sun. Yeah. On the whole, the energy output of the sun does not change all that much. It gets a little hotter, sometimes a little cooler, but relatively speaking, yeah, it's pretty consistent, which is one reason why it's nice for us to live here, right? Our sun is actually a very consistent producer of energy. It does not vary that much in terms of energy output. So it's not like it freezes and cooks us, alternatingly.
All right. Another question was about some of the pictures of the galaxies that you were showing. And I think there was a picture, let me see, let me read out the description,
Okay.
with a large galaxy in the lower left and lots of swirly pale formations across the whole image. Um, and the question about that image was, how is that picture taken without the galaxy and other large parts blowing out the brightness?
Okay. So I did not take this picture. So I don't, the true answer is I don't know because I didn't do it, right? I had credit somewhere on that slide, where the picture came from. But again, this will be a short answer. And we have an imaging group, right, that can go into this stuff in gory detail if you're interested. One short answer I'll give is that, yeah, if you open the shutter actually onto an object for just a really long time, you're going to get some bloat. Certain bright objects will bleed because the way the sensor works, right, it'll actually bleed across different pixels. So one thing that we do is we actually take lots of shorter exposures, right? So it said like 35 hours of total imaging time. I think that's probably the picture you're referring to. And it was not 35 hours of having the shutter open. It was probably hundreds and hundreds of images of having the shutter open a short amount of time. And then they are what we call stacked. So you take these images and then they're digitally combined through a bunch of signal processing. And that removes the noise in the image, right? And can then also highlight contrast very nicely. I hope that made some sense as this quick answer.
Okay. And there was one other question which we sort of answered in the chat itself, but you can add your thoughts on that as well. And the question was that when galaxies collide, what happens? What really happens?
Okay, yeah, so we call it kind of a galaxy collision, but the reality is it's mostly empty space, right? We saw that even within our own solar system. It's a lot of nothing, actually, in our solar system. So when galaxies collide, I mean, somewhere one star could hit another star, but it's actually unlikely. So for the most part, these galaxies will move towards each other, and as they really quote unquote collide, mostly it's gravitational interaction. Stars will be, through the gravitational interaction, be dragged out of their normal positions, And so when we can look at this and we can see these effects in space. We can look at different galaxy structures out there, and we can see some that already have collided. And yeah, they might start out as nice spirals that then come together. Now these spiral galaxies start to interact and they kind of fly through each other, and then they become smeared out because they gravitationally interact and they drag each other's stars around and they become all messy looking. So post-collision galaxies are very blobby, whereas the pristine galaxies have these nice spiral structures. Yeah, so you don't really get star collisions, although it could happen, but for the most part, you just have them really disrupting their internal structures, each other's internal structures through gravitational interaction. Yeah.
Right. Those are all the technical questions so far.
Okay.
We have gotten a lot of positive comments on the presentation, and especially Teresa says that I love all the analogies like telescopes as funnels and elements as
Thanks.
Lego blocks. That will help me remember those ideas. So thanks for that.
Great. Thank you. I appreciate that worked. Good deal. So. All right. Okay,
Yeah, that's it.
I guess that's the show for today. So please check out our meetup calendar for other upcoming events. We're playing this by ear as the coronavirus unfolds, but we're definitely going to be scheduling more online armchair star parties and other things like solar observing on Sundays. So yeah, look for those, and please join us again. Thanks all for your attention tonight. Go ahead, Swami.
Yeah, and there's a follow-up question as to what you just said about the galaxy mergers.
Okay.
And the follow-up question was, do they flatten back out into normal galaxies or stay globby?
No, they stay messed up pretty much. Yeah. So, once they've gotten messed up, that there's really no force that will kind of straighten them out again. Yeah, unfortunately. So we can, so that there's I think it's still there. You can do some citizen science if you want. There's a project called Galaxy Zoo. So Galaxy ZOO Zoo. I think you can just Google for this. And it's a research project where, we have telescopes that take way more pictures of galaxies than we have people to look at. So you can do science. You could visit Galaxy Zoo and help classify galaxies, as to how they look. Like, are they spirals? Are they blobs? Are they this? Are they that? And people actually end up being cited in research papers as a result of this citizen science work. So if you want to see examples of these kinds of different galaxies and even help science, I believe the Galaxy Zoo project is running still, and you could check it out and even participate there. Yeah.
Yep. That's
okay.
it. That's it for now.
All right. Excellent. Thank you, Swami, for your help tonight. I really appreciate it. And thank you all out there for sticking with us through this hour. I realize I actually went over a little bit, but I hope you got something out of it. Thanks. Have a good weekend. Until next time.
All right. Bye-bye.
Bye-bye.